Voila. Here it is. So today's speaker is Dan Baxter. He obtained the PhD from Northwestern University, working on the PICO collaboration. Spent a lot of his year at SNOLAB commissioning PICO 60 detector. Since then, has been a KICP postdoctoral fellow at the Valley Institute of Cosmological Physics at the University of Chicago on working on the DAMIC experiment. Help leading the analysis of the final result from DAMIC at SNOLAB, which is presented on today, and is the low background task leader for the future DAMIC-M experiment. So I'll give you the stage. Go then.
Okay.
Thank you.
Thank you very much, Sylvia, for the introduction, and thank you everyone for having me. This is a particularly this means a lot to me to be able to come back to SNOLAB to give a talk on my research, since as Sylvia mentioned, I spent quite a lot of my PhD there, and so it's nice to see a lot of friendly, well, not faces but names on the call, and I'm just really happy to be here. So today I'm going to be talking to you about latest results from the full exposure of DAMIC at SNOLAB, which we put out in July, so very recently. And I guess I should mention have since been accepted for publication in PRL, so you can expect that soon. So before I go any further, I have to give an obligatory slide on dark matter, even though I expect most of the people on the call know what dark matter is. All I will say on this is that at this point, there is an overwhelming amount of evidence that dark matter exists. This goes as far back as galaxy rotation curves, or as recent as measurements of the anisotropy of the CMB. And there's many, many more types of evidence for dark matter. I don't have time to get into it in this talk, but basically all of these things tell us a few pieces of information about dark matter. We know that it makes up about 27% of the energy density of the universe. It does interact gravitationally, hence the word matter, and it does not interact through the electromagnetic force, hence the word dark, or at least not strongly through the electromagnetic force. There are some reasons to think that it might have some other interaction with standard model particles, but that interaction would have to be very small. And so two of the leading candidates, if that is true, are weakly interacting massive particles, or WIMPs, and axions. What I'm going to be talking to you today is WIMPs. I'm not going to have time to touch on axions at all. And if there is some weak interaction between dark matter and standard model particles, that means we can build a detector to go look for it. And what I mean is best described through this diagram on the right, where you can just draw a particle physics diagram between dark matter particles and standard model particles. And if you think of this as going left to right, you have two dark matter particles annihilating into standard model particles. This is what you would look for in what is called an indirect detection experiment, or, for example, what happens in the early universe through thermal freeze-out models. You can flip that the other way and read this from right to left, and instead think about very high energy standard model particles colliding and producing dark matter. This is what we think about when we talk about a search for dark matter at the LHC. What I'm going to talk about today is direct detection, where instead we have a standard model particle detector, and we look for the very small energy deposition that happens when a dark matter particle scatters off of the standard model particles in that detector and deposits some small amount of energy and momentum. Now, this can happen in essentially two ways. You can either scatter off of nuclei, in which we can typically consider elastic nuclear scattering. This is what we think of as the standard WIMP paradigm. And in particular, we're going to be talking then about masses of dark matter between about 1 and 1,000 GeV. For those masses in a standard nuclear size, this means we're going to be talking about 0.3 to 300 keV of recoil energy. So we need to build very, very sensitive detectors to measure this. Alternatively, and I'm not going to talk about this as much today, you can think about scattering off of the electrons in your detector. In that case, you have sensitivity to lower mass dark matter, about 1 to 1,000 MeV in dark matter mass. And the energy deposition in your detector is going to be even lower, about 1 to 100 EV of recoil energy. To give a brief overview of my talk for today, though, I'm going to start by talking about how we try to build a direct detection experiment using charge-coupled devices, or CCDs. I will then get into a little more detail on our experiment in particular, which is the DAMIC-M detector. I'll give an overview on the previous results that this detector has put out over the last 5 years, since we have a wealth of results that have come out of this. And then I'll talk about constructing a radioactive background model for the detector, which directly leads into the new results from DAMIC at SNOLAB, which I'll be presenting today and concluding my talk with. But before I go any further, I have to acknowledge that I am here representing the broader DAMIC collaboration, and I'm very honored to be representing this international group of people who are working with CCDs to better understand dark matter. So what is a charge-coupled device? Essentially, all it is a silicon wafer where you can have some particle, let's call that particle chi, come into your silicon detector, strike a silicon nucleus, and produce some number of charge hole pairs. Those charge hole pairs then can be drifted across the silicon substrate using an electric field, where the holes will be drifted upwards and the charges will be drifted downwards and discarded. For the sake of simplicity, I will talk about collecting and measuring charge, but what we actually collect are holes. So from there, you can use what you see at the top as this three-phase gate structure, where you can ensure that one of the gate potentials is lower than the two around it. So in this case, phi2 is lower than phi3 and phi1. If you set up the detector in this way, what this means is that the charges will preferentially collect under this lower gate potential, and they can be stored there for a very long time. Until eventually, you can shift these gate potentials such that now phi3 is lower than phi1 and phi2, and the charges are moved laterally. So this is how pixels are moved from the pixel they're collected in until ultimately the readout stage of the detector. So we shift the charges laterally until they reach the serial register, and then again until they reach the readout amplifier. What this looks like more physically, if we take a CCD itself, this is a 1K by 6K CCD. So you have some number of charges that are stored in a pixel. You clock those gate potentials such that they move laterally into your serial register. And then you clock the serial register in the same way, such that these charges move down into your readout amplifier. And at the basic level, this is how a CCD works. Obviously, these pixels are not to size, as our pixels are 15 by 15 microns squared. However, at the readout amplifier, we then need to account for the readout noise, which is measured for the DAMIC at SNOLAB CCDs to be less than 2 electrons for one pixel, an individual pixel readout. And keep in mind, these are more than megapixel CCDs, depending on the size that we're talking about. So if we want to run a CCD at low energies, we need a way to get around this readout noise. And there's essentially two ways that you can do that. Option one is to develop a new type of amplifier with lower readout noise. This is what is done in the case of skipper CCDs, which I'll talk a little bit about at the very end of the talk, because this is really the future of the CCD program for both Sensei and DAMIC-M. But option two is to just downsample the pixel array to trade position resolution for readout noise. And this is what we've done for all of the data that I'll show you today. We have specifically downsampled by a factor of 100 in Y to reduce the readout noise at the cost of position information in that direction. So to summarize, you have an interaction in the silicon which produces free charge carriers that are then drifted across the fully depleted bulk silicon region with very little loss of charge, collected in 15 micron square pixels, which gives you exceptional position resolution, and stored for a user-defined readout time of many hours, which gives us the large exposures that are needed for a dark matter search. And again, we can choose the readout method to optimize our readout noise at the cost of position resolution. And in our case, we choose what we call 1 by 100 binning. Now, what we actually measure then is essentially a stacked two-dimensional histogram of charges measured for each pixel in the detector. And so we take this image, and this gives us a lot of information about the events that are deposited in the detector. Now, in particular, because of our position resolution that's on the order of 15 microns, higher energy recoils, for example, this is a 41 keV beta, are going to give us longer tracks. So this is true for high energy electron recoils or for muons. In the image to the right here, you can see that in the case of an alpha, because this is extremely high energy at the order of MeV, we're going to get a very large blob of energy deposition. And the profile of these events is actually going to help you identify the progenitor event, which is very important for identifying and rejecting background sources. Now, when you get to low energies, the energy deposition of the event appears point-like on the scale of the pixel size. However, we can still use information of the CCD to tell a lot about this, because if you have an energy deposition at a depth z, what you find is that as the charges drift across the silicon bulk, they experience lateral thermal diffusion, lateral thermal motion or diffusion, proportional to the vertical distance that they travel. And we measure this on the pixel array as the spread of charges in the reconstructed cluster. You can see that for this low energy beta here, which is about 4 keV, where we measure the lateral spread in X and Y in what we call sigma. And so this tells us directly something about the depth of the event in our detector. And this is going to become very important for constructing a background model. So to model this, we actually use muons with surface data of the same CCDs, because they give us an excellent depth calibration of this lateral charge spread. And you can see that very nicely on the bottom right plot here, where if, for example, we have a muon entering a CCD in the front at z equals 0 and traveling in a straight path to the back of the CCD at ZD, you can see very clearly the relationship between depth and the charge spread of the track. And so this gives us a really excellent calibration of this effect, which allows us to construct a model that relates our reconstructed lateral spread of the charges on the CCD, again, which we call sigma, with true depth of the event in the detector Z. And this is going to become very important later in the talk when I talk about building a background model. So this is great, but nothing I've shown you so far is new. All of this we knew how to do even in the prototype run at SNOLAB back in 2016, where you can see here our data in terms of lateral spread sigma and energy, reconstructed energy, where we were able to place fiducial cuts on the detector to use this lateral spread variable to isolate a relatively low background region of the silicon bulk, cutting out surface events on the back and front of the detector. And so you can see those fiducial cuts here in a projection on the sigma axis. And we were actually able to use this to produce extremely competitive results despite only having 0.6 kilogram days of exposure, which is about a factor of 100 less than other experiments setting limits in the same region. And so this prototype detector successfully demonstrated the ability of a low threshold CCD array to search for dark matter. But I will note the prototype run of DAMIC at SNOLAB never held more than 9 grams of CCDs total, with a fiducialized background rate of approximately 15 counts per kilogram per day per keV. Because that's a mouthful to say, we typically abbreviate that unit as a DRU, or a differential rate unit, which I will be referring back to for the rest of the talk. What I'm going to talk to you about today is actually the upgrade of the DAMIC at SNOLAB detector, which now contains 17 16 megapixel active CCDs for a total mass of 42 grams, over 300 cumulative days of exposure, and a significantly lower background rate due to the addition of an ancient lead shield for a fiducialized background rate of about 4 DRU. And in particular, one CCD, which I'll refer to throughout the talk as extension 1, is held in an electroformed copper module and surrounded by lead bricks, which gives it a fiducialized background rate of 2 DRU, almost an order of magnitude lower than the prototype run. So just to sort of highlight the data that we took, we characterized the detector for most of the first part of 2017, taking some alpha data that I'll talk about very, very briefly later in the talk. But most of the science data that I'm going to be referring to in the result that we presented was taken between September of 2017 and January of 2019. And again, you can see that here is the 1/100 data. We took LED calibration data throughout, and there were really quite minimal interruptions to this run due to temperature, radon, or power issues. This is what the CCDs in this detector look like. They are 6 by 6 centimeters squared for a total of approximately 4,000 by 4,000 pixels. The pixel size, as I mentioned, is 15 by 15 microns with an approximate depth of 675 microns. We cool these CCDs to 140 Kelvin and read each one out with an individual Kapton flex cable per CCD. The dominant intrinsic background for this run is expected to be tritium production from a direct activation of the silicon wafers before they were turned into CCDs. And this is because the silicon wafers that were used to make these CCDs were not controlled prior to production. And so this is very much expected to be the dominant background. And this is what the inner detector actually looks like. So you can see a very nice picture on the left here, underground at SNOLAB, which is our copper box, which acts as an IR shield for these CCDs. You can see these slots at the bottom where we place the CCD modules themselves. In the middle, you can see that we have 6 modules installed at the bottom and 1 module installed at the top between these lead bricks. I'll just remind you that this is our low background CCD, extension 1, and these are the other 6. This is what it looks like sealed up with the front plate placed on and the cable run out the top. And then, of course, we install this inside of a cryostat and surround it with lead before dropping it into a larger lead shield. All sealed up in the J-drift, you can see this is what it looks like, where we place this inside of a lead shield, as I mentioned, which gives us excellent gamma shielding, and a polyethylene shield outside of that to shield neutrons. And with this detector, we've produced a number of excellent results. 2 of these results, which didn't come out of the SNOLAB detector itself, but calibrations to inform it, are a measurement of Compton scattering and a measurement of nuclear recoil ionization efficiency, both of which I'll talk about briefly on the next slides. As far as background goes, we used the prototype detector to characterize CCD backgrounds for the first time back in 2015. And more recently, we have used a really unique feature of the CCDs, which I'll talk about briefly, called a coincidence analysis, to constrain intrinsic backgrounds to the bulk of the silicon. And I'll mention this when we get there, but there's a paper posting to the archive either this week or next. And then for this dark matter result, we actually produced a full radioactive background model of the detector for the first time. And a longer paper on that is in preparation with hope to submit to the archive and to a journal by the end of this year. As far as dark matter results go, we had initial dark matter nucleon scattering limits, which I already showed you back in 2016. We produced limits on hidden photons, dark matter electron scattering as well. And last, the full exposure dark matter nucleon scattering limits, which are the feature of the talk I'm here giving today. So before I get more into the main limits, I do want to summarize some of the previous results because they are important to characterize the new result. So in particular, I'll start by highlighting this Compton scattering measurement, where you can see here we used a cobalt-57 source with a CCD at the University of Chicago to validate the energy response of these CCDs, and specifically that we can simulate that energy response very well when exposed to a known gamma spectrum. And so you can see here with data in blue and simulation in red, excellent agreement across all energies, even down to very, very low energies in these CCDs. And so this is a really excellent validation that we can actually use simulation to construct a background model for these detectors because we understand their response quite well. Moreover, we can look at that same data. Again, this is cobalt-57, and we can look at the lateral spread of events in that data and compare between the lateral spread that we get with our diffusion model applied to simulation versus what we actually measure. And what we find, again, is excellent agreement between our diffusion model and the actual data. And so this is a comparatively important verification that we actually can simulate, in addition to the energy response of these CCDs, the lateral spread that we measure on the pixel array, which we use as a proxy for depth. And we've shown that this agrees very well, not only for gammas, but also for neutrons. On top of that, I mentioned our nuclear recoil ionization efficiency, where for antimony beryllium neutrons, which have an energy less than 24 keV, we've shown that down to nuclear recoil energies of almost a keV, actually for this antimony beryllium data, it goes down to about 600 or 700 EV. We are able to calibrate what fraction of that energy will be available as ionization down to a threshold of about 60 EV. And that's very important because our ionization threshold for this data is going to be 50 EV. And so this means that we have fully calibrated the nuclear recoil response of these detectors, essentially all the way down to our threshold. Last, I should mention that DAMIC at SNOLAB has reported the lowest published dark current of any silicon experiment at the time, of about 2 × 10⁻22 amps per centimeter squared. And I will note that since this result, which was published back in 2019, Sensei has since basically achieved a comparable dark rate using skipper CCDs. And this is really evidence that CCDs are the leading technology for these really low threshold single electron measurements. And I'll talk a little bit more about skipper CCDs again at the end of the talk. But we used this extremely low dark rate to set competitive and actually world-leading limits on dark matter masses less than 10 MeV using dark matter electron scattering. And at the time, as I mentioned in 2017, these were the world-leading limits. Since then, Sensei has released undergrad results, which are slightly better at higher masses, but equivalent with our earlier result at lower masses. But what I'm here to talk to you about today is not all of that. I'm here to talk to you about the new results from the full exposure of DAMIC at SNOLAB. And so before I start talking about that, I need to talk about our background model. And the reason that's important is that if you look at this 2016 result, what you see is that as you go down in energy, these simulated surface events begin to bleed over the fiducial cut, both in the front of the detector and in the back. And that's very important because what that means is that at low energies, like we want to use for our threshold of 50 EV, the difference between bulk and surface events becomes less clear. And that means we can't rely on a straight fiducial cut. We're going to actually need a background model for this data. So to do that, we begin by categorizing which detector backgrounds we care about. So for this detector, we are completely dominated by electron recoil backgrounds. For those who don't know the terminology, that means we're going to mainly care about gammas and betas. The assumption here is that neutron, muon, and alpha induced backgrounds are going to be completely subdominant. From there, we're going to simulate all of our detector components for these backgrounds. Again, this has the assumption that GEANT4 accurately simulates all relevant decays down to our threshold. And we're confident in this because of the Compton measurements that I showed you earlier, which agree very well with our simulation, both in energy response and lateral spread sigma. From there, we'll choose an energy region of interest that we will want to look for dark matter in. In our case, this is going to be 50 EV to 6 keV. The threshold of 50 EV is set because our reconstruction efficiency drops below 10% below that. And the maximum of 6 keV is set because above that energy, you mostly only have sensitivity to dark matter heavier than 10 GeV, which has been largely excluded by other experiments. We're going to set aside some amount of data as a check, and we're going to choose extension 1 because since it's sandwiched between those two lead bricks, it has a significantly different background environment. And so that makes it a very nice check on our background model construction. And last, in order to construct that background then, we're going to perform a fit against data in the energy region of 6 to 20 keV, which you will note has no overlap with our region of interest. And the assumption here is that there is no dark matter sensitivity in this mass range, again, because dark matter masses greater than 10 GeV for these cross sections have been largely excluded. And the maximum of 20 keV is chosen because we want to include the full tritium spectrum all the way out to the endpoint of 18.6 keV. So this is what the GEANT4 geometry of the inner detector looks like. I'm stripping off the cryostat and the outer lead shielding so that you can see. We have the 2 lead bricks sandwiching our electroformed copper module here, along with our 6 normal copper modules with CCDs down here, stored inside of a copper box, which does have a lid in the simulation, just removed for being able to see this, surrounded by lead, and placed inside of our outer lead shielding. In order to construct the background model, we're going to consider a number of different isotopes. We're going to consider the full uranium and thorium chains, including lead-210. We do not assume secular equilibrium in the uranium chain. We assume that that is broken at radium-226 and at lead-210. We assume potassium-40 could be a major contributor, as well as activation of the copper components and silicon-32 intrinsic to the wafers themselves. Additionally, we allow for activation of the silicon to produce tritium and sodium-22, which will be in the bulk of the CCDs. So from there, we need to construct our CCD geometry. So this picture is very much not to scale, but basically you have your active bulk region and then some very interesting surface features. So we put quite a lot of time in this analysis into understanding the surface features of our detectors, in particular into understanding the back. And the specific reason for that is this gettering layer, which is a key piece of the construction of these CCDs, and it's part of the reason that these CCDs function as well as they do, is that this is precisely the layer that gets or removes heavy metal impurities during the CCD production, which gives you a very pure silicon bulk. However, it also traps a number of other things, and so we wanted to know if the presence of this gettering layer would be a problem from a radioactive background perspective, which I'll talk about in a minute. Outside of that, we have a number of layers of silicon nitride, silicon oxide, and polysilicon, all of which basically form the backside contact structure. So what we did was we performed a secondary ion mass spectrometry, or SIMS measurement, from the back of the CCD, so going into the detector, where you can see the approximate depth in the detector here. And we measured the concentration of phosphorus, hydrogen, and oxygen as we went from the outside of the detector inwards. And what we found was very interesting. So first, what we found is that the gettering layer, in addition to getting heavy metal impurities, also gets hydrogen. For anyone who is versed in low backgrounds, this is super, super concerning because where there is hydrogen, there is tritium, and tritium is always going to give you low background events. I won't really talk about that too much more because for this analysis, actually, it looks like the tritium contribution to our backgrounds is going to be subdominant to one other effect that I'll talk about on the next slide. But for future detectors, this is something that we are very worried about. The more interesting thing with this measurement for the DAMIC at SNOLAB data actually came from the phosphorus measurement, where we found that the phosphorus distribution down to the fully depleted bulk, which has a phosphorus concentration of about 1 × 10⁻11 atoms per cubic centimeter, is very slow. And in particular, it happens over the course of about 10 microns. And so what that means is basically this phosphorus slope tells you the change between where you have 0 charge collection efficiency out here and full charge collection efficiency in the bulk. But the fact that this slope is so gradual means that we are going to have a non-negligible partial charge collection region in these CCDs. And so what this looks like, as far as collection efficiency with depth goes, where I've kept the x-axis, the depth axis here, the same, is that as you move in from what was the original wafer surface, which is at the edge of the gettering layer, you move from 0% charge collection efficiency to 100%. And just because of that phosphorus profile, which I showed you on the last slide, and I don't have time to get into this very technical calculation here, you find that that transition happens over the course of roughly 5 to 6 microns. The reason that turns out to be a huge problem for the DAMIC and SNOLAB CCDs is that this surface right here was never treated. And in particular, these wafers were stored exposed to air in a warehouse for about 3 years before they were made into CCDs. And so that means we can expect to have a substantial amount of lead-210 deposited on this surface right at the edge of our partial charge collection region, which means we're going to get a lot of low energy betas moving through this area. As far as what that looks like, if we just take lead-210 simulated in that exact spot, and if we assume a step function in collection efficiency at the wafer surface versus a model that looks like this, what we find is a substantial difference where the partial charge collection region actually takes events that would be higher energies and shifts them down into this spike here. And so the partial charge collection efficiency effectively moves all of your events down into your region of interest. So as you might imagine, this is very concerning. And I will talk about later in the talk how we got around this. But this was a challenge that took quite some time to address in the analysis. Good, so we have all of these simulations then, including the surface and bulk simulations of the isotopes I talk about. Each isotope is individually simulated for each detector volume, and the energy and position of each energy deposition is recorded. We then apply the diffusion model that I showed you at the front of the talk, which is built off of muon calibration data, which you can see takes this original energy deposition and it basically gives it this lateral spread on the pixel array based on the depth of the event in the detector. Because we're doing this 1/100 binning, we then take that event and bin it according to what we expect to actually measure. And then we paste that onto some randomly sampled noise. And so this gives us what looks like a simulated event in terms of what it should look like from a reconstructed standpoint. We then constrain all of these simulations with material assays. So we have assayed all components near the CCDs to the level at which they were simulated to contribute 1 DRU to our background. And that's 1 DRU is effectively 10% of the total background rate that we expect. And actually the CCD activities that we use in this analysis are going to come from a direct analysis of the data itself, which puts far stronger constraints on them than the assays that we can perform using ICP-MS or germanium counting. And so I'll talk about that in a little bit. But in general, you see that almost all isotopes are very well constrained, at least by an upper limit in our detector. And so one of the really unique features about CCDs, which I think makes them one of the most promising technologies for the future, is their exceptional position resolution. Because what this means is, because this is a solid state detector, if you measure an event that happens within a 15×15 micron location in the detector, and then 2 months later, you measure an event happening from that same spot, statistically speaking, that cannot be dark matter. The probability of dark matter interacting in the same place twice is virtually 0. However, if you have, for example, silicon-32 in the bulk of your detector, which you do because it's built of silicon, those decays are going to happen with a half-life of 14 days apart, but in the same location. And so what this means is we can do what we call a coincidence analysis, where we look for decays happening in the same location in the CCD over long time differences. And we can use this to make very precise measurements of bulk contamination using the detector itself, and actually removing these events in the case of where one of them is low energy, because we know that that then came from a decay chain sequence. And here are 2 examples, which we'll be putting out in a paper, again, that hopefully will go to the archive this week, but possibly next week, depending on internal approval, where you can see on the left here, we have a beta decay that happens with 57 keV, followed by a second beta 1.4 days later, that is 370 keV. Or even more interestingly, this event on the right, where we have a 77 keV beta here, where 14 days later, so 2 weeks, you get a 400 keV beta happening from the exact same spot. And I'll just point out for this one on the left, this is particularly interesting because if you look at the Q values of these decays, that first beta for the second event, which is 77 keV, is above the Q value of lead-210, which means we can actually definitively say that that right event is a silicon-32 phosphorus-32 coincidence. We can not only say that this isn't dark matter, but we can say definitively that this event on the right was silicon-32 and phosphorus-32. And so I just want to emphasize that that's really an amazing feature of these CCDs that, to my knowledge, no one else can do. And so look forward to our paper, but the constraints that we will be putting on intrinsic bulk silicon contamination, we can set silicon-32 levels. We actually measure them to be about 140 microbecquerel per kilogram. We can set lead-210 bulk levels at less than 170 microbecquerel per kilogram, which is far more sensitive than any other bulk lead-210 measurement technique I'm aware of. And uranium and thorium sensitivities that are comparable to even the best ICP-MS sensitivities. So this is a really astounding feature of these CCDs. But back to the analysis. So this leaves us with over 1,000 clustered simulation outputs for various isotopes and volumes in the detector, which is over many, many terabytes of data. So this is way too many to perform a fit against because that would take forever. So instead, what we do is we take the clustered energy and sigma outputs and combine them into 48 two-dimensional templates in energy and sigma, according to common material origin and isotope decay chain. We then fit these templates to data above 6 keV, so specifically between 6 and 20 keV, to give us then a prediction at low energies of how to combine these templates in the region of interest. I'll note that we remove the fluorescence lines, both for copper and silicon, because we've had trouble reproducing those in the past, and we don't want them to incorrectly bias our result. But essentially, this gives us a single PDF in simulated coordinates for the region of interest below 6 keV that we can then translate into reconstructed coordinates. So to do this fit, we perform a 2D template likelihood fit in energy and sigma space. Functionally speaking, this is extremely similar to the fits that are done to the excess at the galactic center in indirect detection searches, if anyone is familiar with those, where essentially we just assume a Poissonian distribution of counts in each bin in energy and sigma, where the number of expected counts is according to the sum over all simulations, where each simulation is given some scale parameter, which the fit is allowed to move up and down. And depending on the measurement of the activities in that isotope part combination, that parameter is constrained either by an upper bound or by a Gaussian constraint in the likelihood function. And essentially then we can perform that fit against data shown here, and we get a simulated result. And so this is the combination of all 48 templates when fit to that data. And as you can see, just flipping back and forth really quick, you can see that all of the primary features of this data are maintained in our simulation. So this is very exciting. This means that it worked. And this allows us to combine the raw output of the simulations in simulated energy and simulated depth all the way from 0 to 20 keV, where again, we fit in this region above 6 keV, but the region we care about is this low energy region below 6 keV. The result of that fit is that we find 30% of our background to come from the CCD bulk dominated by tritium production. This is, again, what we expected based on the history of the wafers. And 15% of the background comes from lead-210 on the back of the wafer surface. So that's right at that partial charge collection region that I mentioned before. 10% of the background is going to come from lead-210 on the outer CCD surfaces. So that's essentially the front surface. From deposition at SNOLAB before these were installed. And approximately 30% comes from the OFHC copper, mainly from activation and primordial decay chains, but also lead-210. And then the remaining 15% is just sort of a mixed bag of other stuff, Kapton cables, lead, and so on.
And this is what the energy projection of that fit looks like. I'm extending it down to lower energies, but again, you can draw a line at 6 keV and say that the fit is done up here. And you see really excellent agreement across all energies. Again, we don't fit to the copper fluorescence, which is why there's poor agreement there. But you can see very well that we reproduce the lead peaks at 11 and 13 keV from those X-rays. And that we do observe in data a sort of rise as we go to lower energies due to tritium. And so this is, I'm already showing you some of our dark matter search here because I'm showing you less than 6 keV. But in general, we get excellent agreement between our data and our background model all the way down to essentially 200 EV. And so here I'm showing you the same thing, but now projected on sigma, where you can see for the region above 6 keV in red and the region below in blue, we have very excellent agreement at all energy ranges on these plots. And you can ignore everything below 0.1 pixels. And if anyone wants to ask later, I'll say why, but it's complicated and not important. Very good. So this leaves us to a very important point, which is that we now have a background model. However, 15% of our background is from this lead-210 right at the partial charge collection region. So you should ask the question, well, how well do we understand the systematic uncertainties in our model for charge reconstruction in that region? And the answer is that we were very worried about this, but we found something quite fascinating, which is that the reconstructed spectrum that we get essentially to first order only depends on where this endpoint is. And so if you move this 0 point left and right, we find that this can be parameterized with an exponential that goes like the square root of energy over alpha. And this was true for every variation of the partial charge collection model that we tried, which means that basically we were able to encode this into our dark matter search as an extra parameterized component. And this is really important as well, because this partial charge collection region, while it shifts things to lower energies, is still located on the back of the CCD. And that means we can still use information about the lateral spread. And in particular, if we look at low energies where we expect a bulk signal to appear, there's excellent separation between something happening in the back of the CCD, as in the partial charge collection region, and something happening in the bulk. And so even though we do have this large systematic uncertainty and exactly how much of this component to include, we do have a very strong constraint on signal because of the separation in this two-dimensional space. And this is excellent because it means we don't need to have a fiducial cut. So again, this is the simulation output, which I mentioned. We now need a way to reconstruct the region of interest for this simulated background model into reconstructed coordinates exactly like data. And so to do that, we take these simulated true variables and we actually randomly sample the PDF that I showed you on the last slide and apply our diffusion model directly to translate that into a pixel spread and paste those pixel spreads onto what we call blank images, which are images with 0 exposure. So they just have the actual readout time of the detector. And then run our full clustering algorithm on those simulated images to reconstruct a basically exact replica of what an analysis would produce for those events. And this allows a direct comparison for events below 6 keV with data. And you can see here, for example, this is one event in data, which we measure right here. You can see it is about 25 charge event that is in basically 2 pixels. And you can even see by eye that it is clearly there. So because we paste these on blanks and then run our actual analysis code on it, this means that we are implicitly encoding all of our reconstruction efficiencies in the background model, just like for the data. And so that's a nice added feature of this way of doing the analysis.
But additionally, other pieces of the analysis, which I'll just sort of skim over before getting to the result, we mask hot regions of the CCD, which contain higher dark current. We scan over the image and perform a likelihood ratio test to find clusters, which is our complicated cluster finding algorithm. And then this essentially gives us full efficiency down to 100 EV, and then, as I mentioned, drops off to 10% by 50 EV. So this is very good. We do this. This is the background model that we get after that procedure, which we can then use to directly compare against the data in this region of interest to either search for or set limits on dark matter. So we do this. We build an extended maximum likelihood function, and I think I'm going to skip this technical slide to end on time. And this is the fit result. We find exceptionally good agreement at energies greater than 200 EV between the background model and signal, with a small excess at low energies. And so I'll zoom in a bit on that excess, first in two-dimensional space, because that's what we actually perform the fit in. So we see this red contour here represents the best fit exponential excess at low energies that we observe. And the blue circles are the actual events in our data, overlaid on the background model expectation and the expected number of events per bin in gray. And so we do observe this excess. We do not report it as a WIMP signal for a number of reasons that I'll talk about later. But just to look at it a little more closely, this is now zooming in on the low energy region. So I'm cutting off this plot at 1 keV. You can see that most of that excess is happening below 200 EV. And in the energy projection alone, it is not particularly convincing, if I may say. Blue here is a background model only fit, and red is background model plus signal. However, if you look at this in the sigma projection, you can see that the reason the fit prefers a signal is that the background model dramatically underestimates the number of events observed in what basically gets reconstructed for these energies as the bulk or front of the detector, and slightly overestimates the back component, which gets subtracted off using our free parameter that encodes the partial charge collection uncertainty. But regardless, even though we have this excess, we are able to set strong limits on WIMP dark matter, shown here. You can see our projected sensitivity in this red band. And at higher masses, we are able to meet that sensitivity, which allows us to exclude a significant fraction of the CDMS2 silicon allowed region. And as we get down in dark matter mass, that signal excess that we observe starts to limit our sensitivity, and you see a deviation from our projected sensitivity here. But we are comparably sensitive with all other experiments in this region, and we have improved our experimental sensitivity by an order of magnitude over the 2016 prototype result. And the basic thing that I want you to take away from here is that DAMIC phase 1 is now complete. So DAMIC at SNOLAB was the first CCD dark matter array ever built. We improved the limits by a factor of 10 over the prototype detector and excluded a significant fraction of the CDMS2 silicon allowed region. Inevitably, we were going to have some surprises along the way, since, again, this was the first detector of its type. And we learned an incredible amount about how low background CCDs work. But the key takeaway is that skipper CCDs are the future. So what is a skipper CCD? Skipper CCDs are basically the same thing I've been talking about today, but with a different readout amplifier that allows you extremely improved resolution so as to identify the number of electrons in a peak. And so you can see here on the right with a CCD in Chicago, we've demonstrated that we can measure a single electron with 0.07 electron sensitivity and very clearly separate the noise, single electron, 2 electron peaks, all the way out to, n electrons. And so the next step is to verify this signal excess that we've observed. So we are currently working on an upgrade of the SNOLAB detector to install skipper CCDs. This will enable another measurement with the same with a lower threshold because of the skipper CCDs in the same now well-characterized background environment. And so if this is a threshold effect, because it occurs right at our detector threshold, this means it should go away. And if it's a missing component in our background model, we will have significantly more events with which to study. But on the right here, you can essentially see our best fit contour for the number of excess signal events as a function of the exponential decay constant of the excess. And this is what it looks like if you just project it on the energy axis, which again is collapsing some very important information in sigma. But we will be able to test this with the SNOLAB detector. How do we interpret this excess? So I think there are a number of possibilities which we need to rule out in order to get to the more interesting ones. I think the first four that we need to address are, we could be missing a bulk component in our background model. We could be missing a front component in our background model. We could be incorrectly modeling detector threshold effects, or missing a front detector effect that isn't accounted for. And only if we can exclude those four options, we can then start considering that maybe we're observing new interesting silicon physics, and maybe we could be seeing some type of dark matter interaction. But we have a lot of work still to go before we get there. And so I'll just very briefly, in my conclusion, talk about the future of the CCD program. So we have significantly improved the reach of CCDs from the original prototype detector at SNOLAB in 2016 to this new 2020 result. The next step is with Skipper CCDs, which have already been pioneered by Sensei, which will achieve single electron threshold over the next few years, but significantly, excuse me, improving limits with lower threshold. The next step after that is DAMIC-M, which will apply the same Skipper CCDs with single electron threshold with additional background mitigation to achieve a hopefully over roughly 100 times sensitivity improvement due to lower backgrounds. And then finally, over the next decade, there is the now Basic Research Needs funded R&D effort, Ascura, which will push the CCD technology to its limit with a 10 kilogram detector array, again, over the next decade. So that's the long term. And you can see here that as each of these steps is implemented, we will encompass a significant portion of the parameter space for dark matter electron scattering and many other dark matter models. So just two more slides. So I'll say, looking to the future, we are currently constructing the prototype DAMIC-M detector, which we call the low background chamber, or LBC, where we will test this the same excess in a different background environment. This is designed to be a roughly 10 times lower background environment than DAMIC at SNOLAB. It will be deployed with 25 grams of low background Skipper CCDs and has a goal of a 1 DRU and 2 electron threshold. And we plan to construct everything in early 2021. All of the parts are basically sitting at Modan waiting for someone to be able to go. And the DAMIC-M detector will achieve a background-free exposure of 1 kilogram a year for the first time with a silicon detector, above a threshold of 2 electrons using Skipper CCDs. And so in conclusion, I'll just say that DAMIC at SNOLAB continues to produce new interesting results. I'll just emphasize, for example, the nuclear limits I'm talking about today and the electron recoil limits we published last year. Sensei will improve on this using Skipper readout to achieve single electron resolution. DAMIC-M will build on that by lowering backgrounds with a much larger exposure. And then Ascura will push the technology to its limit with 10 kilograms of silicon, a single electron threshold, and 0.01 DRU backgrounds over the next decade. And so with that, I'll just say thank you very much for having me. And I look forward to answering your questions.
Thank you very much, Dan. So are there any questions? Fabrice, go ahead. Sorry, I didn't see your hand.
Oh, no, I just put it. I'm trying to get. So thank you. It was an excellent talk. I learned a lot. I have a whole bunch of questions, so I will choose just one. The surface collection issue, have you looked at it with an infrared laser that you could probe different depths and you could look at the charge collection?
We have not. We have, so I don't have anything on this in the slides, I don't think. We have a number of methods we're using to characterize this, including iron 55 X-ray sources. We have not used an infrared laser, but actually what we're doing moving forward is we're just removing it. The large, the slow profile of phosphorus with this method is not necessary for the CCD functioning, and the backside contact can actually be applied over the course of about 100 nanometers. And so what we're working on moving forward is skipper CCDs where the backside contact is completely removed and reapplied after CCD production. And so this
actually just one comment on that. I'm actually working on VUV photon detection, and we want even less than 100 nanometer, more like 5 nanometer of P+ contact.
Ah.
So this exists, even smaller.
That would be great. Maybe we should talk. We were thinking 100, but if you can do 5 nanometers is great. But no, we haven't tried infrared. I mean, that's a great idea. I will think about that.
Thank you.
Next in line is Serge. Go ahead.
Okay. Hello, Ben. Thank you very much for this great talk. It was really very interesting. I have also 2 questions. One question, are you planning to use enriched silicon in order to take away this background in tritium and silicon 33 or 32? Yeah, I believe background. And second question, what was the reason that you select this kind of temperature, working temperature, 140 Kelvin, if I remember correctly? Probably due to the fact that you have the highest mobility of the charge at the temperature. Do I am correct or not? Thanks.
Good. So two excellent questions. So to address the first one, the question is about what we plan to do about tritium and sodium-22 in the bulk moving forward. So as I mentioned with these CCDs, there were basically no controls on the silicon wafers before they were made into CCDs. And so they essentially had 3 years of activation before we even got them. And so with the DAMIC-M CCDs, we're actually limiting their total sea level equivalent exposure to 2 months. And so rather than trying to do anything fancy after the fact, we're just making sure that we very strictly control the amount of activation after the silicon ingot is made. And actually those CCDs are currently, I believe, underground at SNOLAB, avoiding activation, thanks to Ian, who I think brought them underground recently. So we're very grateful to you all for that. But we are currently actually beating our projections for the activation. So we're very happy with that. To your second question about the 140 Kelvin, that is not optimized. That is as cold as we got.
So,
yeah.
But why you are limited to such strange temperature?
Just the that was what we were able to achieve with the cryogenic design of this detector. So for DAMIC-M, we're planning for 100 Kelvin, which is much more optimal for what you were talking about. And so there is a limitation on how cold you can get, which happens somewhere between 70 Kelvin and 100 Kelvin. And so that's sort of why we set that 100 Kelvin as you do get improvement on dark rate the lower you go in temperature, but at some point you lose charge mobility. And so that optimal point needs to be measured and characterized, but we think it should be somewhere around 100 Kelvin. That's something that we're doing research on now. But as far as the 140 Kelvin of DAMIC at SNOLAB, it was low enough for the threshold of the detector, just because with 50 EV threshold, you only need to get dark rate that low in order to not have dark rate leak above threshold. So there wasn't really a need to design the detector to be able to go to lower temperatures. Whereas for future experiments, we are.
Okay, thank you. Thank you.
Chris, if you want, go ahead.
Yeah, thanks once again. Really thorough, good talk. I was curious when you were, like, you showed the turn-on curve for your efficiency as a function of depth.
Yeah.
How, I saw a single curve, but you had like what, 6 or 7 detectors, right?
Good.
Are those blue lines the different detectors?
No, they are different variations in the model that we tried. So this model is calculated based on a lot of information about how for this temperature and for that phosphorus distribution, various parameters that go into this charge model change. And depending on how you move, maybe our temperature reading is off by this amount, or maybe there's this uncertainty in this parameter. These are all variations that you can move that model. And so we were very worried because there's a lot of different parameterizations. You could say maybe the slope is steeper, maybe it's shallower, maybe it's a shift all the way to the left or a shift all the way to the right. And so we tried all of these things. These dotted blue curves are just the things we tried. And what we found is all of them break down to basically to first order just being a function of how much did you move the zero node. And that parameterization of how much you move the zero node can be entirely described with this function. Frankly, we got lucky with that. This would have been an enormously challenging analysis if we couldn't have done that. So I don't know if that addresses your question, but there could be some partial charge collection variation from CCD to CCD. We do not have the statistics to explore that.
Thanks.
Colin?
Yeah, thanks. Great talk, Dan. I just had a couple implementation questions.
Sure.
So you mentioned that you run the detector for a certain period of time. Do you reset it after a certain, collect all your charge after a certain period of time and then start from scratch? And
very good. Yeah, so that's part of the readout. So I didn't get too much into the actual detector readout itself, but that's exactly what we do. We transfer the charge into the readout amplifier, we measure its value, we zero it out, and we keep doing that until we read out every pixel, and then we just reset the whole CCD and start a new exposure.
Okay, and how often does that happen?
The exposures that we were doing for this analysis are on the order of 8 hours.
Okay.
Some of them longer, I think, but yeah.
Okay, thanks. I had one more question if I have time. Also pretty quick. Will DAMIC-M have so in DAMIC SNOLAB, the CCDs were kind of stacked on top of each other.
Mm-hmm.
Will DAMIC-M use the same design, just stacking them? And
that is the plan.
Okay, and is that just easier to cool, or is there a better reason to do that over spreading them out?
It's easier for a lot of reasons. Basically, because the more CCDs you have, the easier it becomes if you stack them, because then you can just sort of lower them into whatever vacuum vessel you have. There is a slight science reason for it as well, because you can use the stack of CCDs to search for things like millicharge particles or things that might interact slightly in each CCD as they go through. And so you can actually look at correlating events across different CCDs in that way. We have also explored the possibility of doing correlated background analyses in the same way. For example, if you have a dust particle on one that undergoes a decay and then a beta that goes up into the CCD above that, can you actually remove both of those? There are some advantages, but from that perspective, that gets into very challenging analyses. From the detector design standpoint, it's just easier.
Okay.
But there aren't really any drawbacks, is what I would say.
Okay, thank you.
There is another question from Alex.
Yeah, I think you were in the process of explaining that, I think. So while you're reading out the data, while you're drifting the charges, how do you, let's say something, some interaction happens while you're drifting, how do you disentangle the pertinent information from the random stuff happening, or is that even possible?
No. So you're exactly right. You don't, and this is very important. So if as you're drifting the charges, your CCD is still live, so you're still collecting.
Yeah.
And so you can't disentangle that. The key though is that at 10 DRU, our backgrounds are so low that we have 1 or 2 events per 8-hour exposure, and the readout time is 5 minutes.
Okay, so then,
yeah,
very low probability.
Very low probability, and also you'll notice we did not use XY information. And so the only concern, if you're not using XY information, the only concern there is that you would have overlap, which we definitely don't care about. And so given that we're not using any XY information, it doesn't really matter if we distort where the event happened in the pixel array if it happens during the readout time.
Right. Okay. Yeah, and you answered my other question. So it's good.
Okay.
But it's an especially important question, Alex, for skippers, because the skipper readout takes a lot longer. And it is a serious problem that you have to address.
I don't see any other hand raised, so I assume that all the questions have been answered. Oh no, there is a go ahead, Gopolang. If I
yeah, sorry, I asked the question in the chat, but I guess I should.
Sorry. Yeah, go ahead.
I was just curious how big the this excess that you saw in DAMIC was, and you said that it was near the threshold, and that you could remove it possibly with including skipper CCDs in DAMIC.
So I missed the beginning of your question. I apologize.
Yeah, I'm just curious how big this excess is.
How big the excess is.
Yeah.
Good. So, I mean, this is the most correct way to show it, because this gives you, I mean, these are the actual parameters that are used in pulling out information about it. So it's about 17 events is the short answer. And most of those events are, I mean to flip through things. Most of those events are clustered around here. So you can see it, right? If you just look at the front here, you have very sparsely populated events, very sparsely populated events, and then a huge increase right here, right? And so there clearly is something happening. And the distribution on the back, you see the same thing. You see this cluster right here. Basically, a significant fraction of these events here and a significant fraction of these events here are what are giving you those 17 events. And so unfortunately, we only showed 3 contours here, 11, 66, and 90, because it gave the nicest image. But if you instead show the full shape, I mean, what it really does is it peaks here and then it dips down almost a lot and then it goes back and right. So there's a really interesting profile. And what's fascinating is the distribution of events in it matches what you would expect from something in the bulk very, very well. And so that's why the background model is not able to eat up these events, is that you pretty much need something in the bulk to do it. And it is large. It's like 60, it's like 17 events.
I see. So I guess what I was wondering is how comparable is it to the excess that was seen by Xenon 1 ton? And since that excess as well was also near the threshold.
Right. So they can't be the same thing. They're very different energies. So I don't think the two are compatible, at least not through standard dark matter interaction models. The two are not compatible. And I think we also looked at whether the two could be compatible through amygdal interpretation of one of them. And that was not compatible either.
I see.
And so we are thinking of this as being either a detector effect or a potential signal independent of what they saw. That we could not think of a collective explanation of the two. Yeah.
Thank you.
As far as significance, I should know this number off the top of my head, and it should be in the slides, but it's not. I think the significance of our excess is something like 3.6 sigma.
No, that's pretty big.
Yeah, but again, that's because it's of this two-dimensional analysis, right? If you just look at energy, you know, it's clearly not 3.6 sigma here.
Right.
But if you factor in that the events happen to be located exactly where they should be, the significance gets quite high.
So does DAMIC have any capability of looking at the electron recoils as well? Because I'm assuming these are nuclear recoils, right?
Yeah, absolutely. So we set strong limits on electron recoils. Actually, until Sensei's results, we were the leading electron recoil limits because we measure ionization. So
Yes, okay.
we actually have better sensitivity to electron recoils than nuclear recoils, because the nuclear recoils get quenched.
Okay.
So yeah, this result came out back in 2019, and we did it first because it was easier. And the nuclear recoil analysis was considerably more complicated because of this excess.
I see. Okay, thank you.
Yeah.
Okay, so I will like to thank Dan again for the very nice talk.
Thank you for having me.
It was great, and talk to you next time. Bye.